At a conference in February of 2020, Andrej, Tesla's AI lead, discussed in some detail the problems and solutions Tesla has experienced creating their amazing autopilot software. Let's take another look at the second half of his talk and find out what he and the team have done. Hey y'all, it's Dr. Know-It-All. If you haven't watched the first half of the two-part video, please check here. In it, I set up the background and some of the elements of how Tesla's autopilot works and how Dr. Karpathy and his team have set up their HydraNet for training. Now let's take a look at the second half of his talk and discuss the amazing particulars of their deep neural network that makes autonomous driving possible. Let's start with what I think is an astounding fact, the AI team's size at Tesla.
And all of this is not maintained by hundreds of people. All of this is maintained by a small elite team of Tesla AI people of basically like a few dozen.
So they have around 40 people? That's just nuts. This is quite possibly the most complex machine learning task ever undertaken, and they only have a team of a few dozen people on it. That's just mind-blowing. Also, I love the term Operation Vacation. In other words, you want to make the machine train itself. This is a really useful way to see how such a small team can and could solve full self-driving, get the machine to train itself. And as we'll find out as we go through the rest of this talk, that's exactly what they're doing.
And there's a process, and we understand how the process for getting a task to work. And we're trying to develop as much automation machinery to actually support the development of these new features and new tasks. And we're removing engineers from that loop so they're not involved. We're just building out infrastructure.
So basically their strategy here is automate, automate, automate. If a recipe for each new training element, in other words, stop signs like we talked about in the first episode, can be created, then you can plug and play each time a new task needs to be accomplished. In other words, even here in software, they are looking to build the machine that builds the machine, as Elon Musk is so wont to say. In other words, they're creating a robust training infrastructure, and the elemental training can happen more or less on its own. A lot of this is in software, as Karpathy discusses, but also just a note, a lot of this is also in hardware. The Dojo supercomputer, which he doesn't really talk about in this talk, probably due to the fact that it's top secret at the time, is a massive part of making this project work in a timely fashion. Definitely check out my episode on Dojo above if you're interested in what the Dojo supercomputer is and will be able to do for Tesla's full self-driving team. This is all fascinating stuff, and it's how one gets from research achievements to building something as complex as full self-driving at scale so it can be released to more than 1 million vehicles. Again, as Elon Musk often says, scaling production is an order of magnitude harder than building a prototype, and clearly this is true for full self-driving software as well.
We're working with caution lights recently. We're trying to detect when the police car lights are turned on. This is an example of a new task that we'd like to know about. And we sort of have a cookie cutter. We know exactly what to kind of approach to. We know exactly what it takes to get a task to work. All the infrastructure is in place. So this task, we're going to treat it as a landmark task. Landmark is an example of a prototype. So we have a detection prototype, a segmentation prototype, a landmark prototype. And these are just classes of tasks. And if your new task is a member of any of these, or an instance of any of these prototype classes, then all of the infrastructure is just plug and play and goes through the full data engine. You can collect the seed data set, you label your examples, you source more examples in the cases where you're failing, you deploy it to in shadow mode, you source examples and you grind up metrics, you create all the unit test predicates. All this is completely automated. And this, we're mostly developing the automation infrastructure, and then it's easy to develop any new task, and that's kind of how we get this to work.
So I find the pseudocode shown here incredibly revealing. It shows a copy and paste kind of recipe of adding basically any feature to their model networks. If a task is a subtask of another that's built already, it basically can inherit all of that information, so it's already partly trained, and that saves a ton of time and makes it really easy because basically you're just taking Lego blocks and you're building things out of that. Super cool idea. So again, I want to stress how important this is. They're not building a new machine, in other words, a new software model for each task. They're building a generalized architecture that you can plug any new case into. This is a massive game-changing way of doing AI work. As a little personal side note, I do 3D animation in my real job, and we do a lot of tech animation, which involves character rigging in my classes. One of my graduates has worked at Industrial Light and Magic, EA Games, Valve, and so on, and when we chat, he talks about how the big issue with production-level animation rigging is to abstract away doing the rigging each time. Instead, they build out an infrastructure where rigs are plug and play. So instead of having to put the skeleton of each character in one at a time, you build out a method to do this automatically. As with the full self-driving software, it takes a ton more time to get this set up initially, but the benefits come in when you have to do the procedure over and over and over. If it's well automated, you make back up that initial time by orders of magnitude once you start to use the automated product at scale. And I know I'm harping on this, but if you only take one thing away from this video, it's that they're building out an infrastructure to automate the task of learning to autonomously drive. That's big stuff. In a moment, let's talk about the way Tesla's team has modified neural networks for full self-driving. But first, if you enjoyed the video, definitely like and subscribe. And also, please do subscribe for the 10,000 subscriber giveaway. You can check that out in the description. If you leave a comment on that video on or before January 5th, which is really soon now, you can win your own, very own sexy coffee mug. And by the way, check out what my wife got me for Christmas. I don't know if you can see it really well. I'll try to go back and forth, but yeah. So maybe if we get to 25,000 subscribers, maybe I'll give away a sexy t-shirt at some point. So you never know. Anyway, so definitely do that if it's on or before the 5th of January. And if it's after that, you can subscribe anyway, because we'll have another giveaway at some other point in the future. Also, a big shout out to my patrons on Patreon. You all are wonderful. Thank you so much for supporting this channel into the new year. I also have a couple of new patrons since last time, Johnny Drimmer and Matt Townsend. Thank you both so much for being part of the team. Also, a big thank you to Zenly Music for doing the intro and conclusion music. He's a great artist. If you want to check him out, search for Zenly Music on YouTube or Instagram. And finally, check out our referral link in the description. If you're in the market for a new Tesla and you use that link, we both get 1,000 free supercharger miles, which is awesome.
And I'm showing the predictions of the road edge task on all of the different cameras. And you can see that this is basically a binary segmentation problem for us. And we detect those edges here, and we use this to wind our way through a parking lot because we'd like to go to a certain destination but avoid all the road edges.
So let's break down this clip a little. What is a binary segmentation problem? Binary is just a 0 or a 1 or a no or a yes. In this case, it means you have to figure out what is curb versus what is road. So the road might be a 1 and the curb a 0, and basically you avoid driving over the zeros in your landscape. But this is not terribly useful if it's only from one camera's perspective, so the next task is to stitch together the views into one map-like view, or bird's eye view as it's often termed. So what this creates is a map like Google Maps or something, but it's drawn in real time and with extreme precision, which it has to be or the car would hit something, obviously.
So the raw detections, we project them out into 3D, and we stitch them up into what we call a occupancy tracker. So this occupancy tracker takes all the raw measurements from the 2D images, we project them out into the world, and we stitch them up across cameras, and we stitch them up across time. So the occupancy tracker is keeping the temporal context of that, and it creates a small local map. So this is all fine, but there's a lot of problems with actually doing the stitching as I'm describing it. I'm making it sound very easy. The problem is these cameras are pointed in arbitrary directions. They make these measurements in these pixel frames. Your road edges might not even align across camera scenes, and writing the tracker for these edges over time is actually highly non-trivial, lots of hyperparameters, error-prone code, very difficult to develop.
So the method being described here is, I guess, traditional in the sense of machine vision. It's what they call an occupancy tracker, or basically where the car is and what's around it, what's safe to drive on and what to avoid, etc., etc. And very importantly, it does this not just in space by stitching together the views of all the cameras, but also in time. This is where the really cool magic starts to happen for Tesla's vision system, and you can see my other video here on 4D projection. First, you'll note that Karpathy says the vision stitching system is highly non-trivial. In normal human speak, that means just about impossible to do. So just note that when people say non-trivial, when they say trivial, they mean hard. When they say non-trivial, they mean really hard. And when they say highly non-trivial, they mean basically impossible. The cameras are facing random directions at space and any time due to the yaw and even the pitch and the roll of the car. And this is changing constantly, so it's really, really difficult.
Where this is sort of the autopilot software stack. On the bottom, you have inputs to the stack, primarily vision. And on the output, we have steering and acceleration. And roughly you can think of two code bases hidden inside the software stack. We have what I refer to as the software 1.0 code, which is good old-fashioned C++, explicitly designed, engineered by a person. Person writes the code. And then you have what I call software 2.0 code, where the code is an outcome of an optimization. It's the compilation. It's a compiler takes your data set and creates neural network code that runs in the car. And so it's, roughly speaking, neural net. The reason I refer to it as software 2.0 is that you can take functionality from 1.0 code base and put it into 2.0 code base. So this boundary is fluid, and you can actually engulf more and more of software 1.0 stack.
From this lovely little image of software 2 kind of eating software 1, we can see what's going on here. Software 1 is more traditional. Each task is hand-coded via C++ to solve a task. Software 2 is the really, really cool stuff we're discussing now. And as you can see, it's basically starting to eat software 1 by taking over task after task. So what does this mean? It means basically that a computer is actually writing the driving code or altering the neural network model based on neural network training. So essentially, when you're driving one of these cars, you're driving a robot that's been programmed by other computers when you use it. And that's kind of a wild thing to think about. And by the way, don't think that this is unique to Tesla. AI is writing its own code a lot now, but it's still pretty darn cool. And as you can also see, of course, software 2 is basically eating software 1. There are a certain number of tasks that have to happen to drive, by yourself, and 2 is basically eating each task up slowly but surely. And eventually it will probably replace all of the hand-coded driving software with optimized neural network-based software instead.
So a lot of our networks have been moving towards these bird's-eye view network predictions, where you take all of these cameras and you feed them through backbones, and then you have a neural net fusion layer that stitches up the feature maps across the different views, and also does the projection from image space to bird's eye view. And then we have a temporal module, potentially, that actually smooths out these predictions. And this is all neural net components. And then we have a BevNet decoder that actually creates the top-down space. And so then we can directly, potentially, predict these road edges in a top-down view.
So what we can see is that this is enabling what Karpathy calls BEVNet or Bird's Eye ViewNet or BevNet or something like that. It's a neural network stack that can encompass all of the functionality of hand-coded elements like occupancy trackers, stop sign identifiers, pedestrian identifiers, and a huge list of other ones. So this image here is probably the most important to take apart a little bit. First, note that Karpathy said potentially for the temporal component. I'm sure that was needed at the time, but now that public Enhanced Navigate on Autopilot beta is out for users to use, it's been explicitly stated that the 4D element is in fact a component, so it's definitely there. So in general, what's happening here? Well, from a bird's eye view, the product is stitching things together in time and space. First, each camera's view is processed via a neural network model. Then there is also a neural network model that fuses or stitches all the camera views together. Then the views are passed through a time-based neural network that is looking ahead and behind for continuity of vision, just as human beings would do using short-term memory. And then finally, the results are processed through a monster BevNet that segments the video, identifies objects, makes predictions, do I need to slow down or turn a little, etc., and passes its outputs to the control system that make the car do something in the next instant.
On the bottom row, on the left, you see the ground truth of what this intersection looks like, and you see that the car is positioned on the dot. And so that's the ground truth. On the very right, you see what happens when you take 2D predictions in the images and you cast them out. You basically get garbage. Like, it somewhat works around the car. There, the projection is easy. But far away, especially near the horizon line, a few pixels of error means lots of meters of error. And so these projection-based techniques are extremely hard to get to work. You'd have to know extremely accurate depth per pixel to do that projection. It's a very hard problem. And in the middle, you are seeing some of our predictions from the recent bird's eye view networks that just kind of make these predictions in top-down view directly.
So again, here you can see that traditional vision approaches, shown on the right, can be extremely poor, especially at longer distances. But through the magic of neural networks, the center representation at the bottom is very close to the ground truth, which is a technical term for the reality of the situation. In other words, if you took a drone up in the sky and took a picture straight down at the intersection, that's what it would look like. So by taking all of the views, stitching them together, and running that through multiple neural networks that are trained to reproduce reality from input images, which is basically what image-oriented neural networks are designed to do, you can almost magically reproduce the actual map of the area from all these disparate views. And by the way, to be able to do this in real time is quite a feat in itself, both for hardware, the inference engine in these cars, and of course for the software as well.
We have road edges in red. We have dividers in green on the very left. Then we have attributes for these dividers. So we want to know if it's an actual curb or if it's just like a logical curb, so like a yellow line or something like that. And then we have a traffic flow direction and a few other things like that. I'm only showing some examples. But the car is on the bottom center of these images. And as we're turning through this intersection, these bird's eye view networks just predict pretty far away the full structure of this intersection and what it looks like.
So this is pretty remarkable. It's all neural network based, no explicit coding involved, and it can do this for many, many road situations, not just an intersection. This is extremely powerful. The same network can be optimized for many situations. You don't have to hand code each possibility, which is the traditional method of doing this. And also, by the way, this is kind of impossible to get to work completely because there are so many possible situations in real life. The potential downside to all this, as Karpathy notes when answering a question after the talk, is that you don't have direct control over the car anymore. Basically, you can't just write a piece of code that says turn left, turn right, whatever. What it means is that the networks can do weird things that are very unexpected. I've seen this in my own research when the network will make what appears to be a bizarre prediction once in a while. When looking at the pictures, this is just kind of a humorous like, oopsie, but if you're driving it, it could be life-threatening. So this is a tough issue to deal with in practical terms. Thus, Software 1 is kind of a box around Software 2, or as Karpathy says, it's a guarding rail around it, to be sure that Software 2 doesn't do anything too bizarre and cause significant problems for the car.
Here's an example of using this for objects. So on the top, we have our camera feeds. On the middle, I'm showing our per pixel depth predictions achieved via self-supervised learning. We need those depth predictions because we take, as many others do in the literature right now, we take a pseudo-LiDAR approach where you basically predict the depth for every single pixel, and you can cast out your pixels, and you basically simulate LiDAR input that way, but it's purely from vision.
And here we have some really cool stuff, the creation of pseudo-LiDAR. And this is why LiDAR is not necessary if you get a vision system actually working. For those of you who are interested, right? Because I know there's a big argument between whether LiDAR is necessary to make full self-driving working or not. So the middle row in this image shows a, quote, LiDAR image of the space around the car, and it's all produced from a vision-only system that's more or less like a human's. We see depth, of course, via the difference between images in our right and left eyes, and the car does this too, only with 8 cameras rather than our 2 eyes.
Of course, no human can annotate depth, so this is done using self-supervised techniques. So in particular, we take an image, we predict a depth. Then when you have a depth for an image, you can cast out all the pixels into 3D, and you can reproject them either into camera views at that same time, but different cameras, or you can reproject them into the future frames of that single camera. And then you have a photometric loss that's enforcing consistency. And so the only way to predict, to make everything consistent in reprojections is to predict the correct depth.
So this is a lot of fun here. What Karpathy is saying is that the network is guessing the depth of each pixel in an image, the Z-space, if you will, away from the camera. And then those predictions are cast out into a virtual world. They create a virtual 3D world around the camera. That 3D world is then back projected to what other cameras would see at the same time, and also what would happen to the objects in the scene over time as the car moves through the scene. And this means that the network can train itself. If it makes a bad prediction from camera A, for example, it will look wrong from camera B's perspective, and it will quickly lose continuity over the next few frames as the car continues to monitor that object. If you can define a good loss function for when the network predicts wrong, which is not a trivial task by any means, and you can throw a ton of real-world video examples at it and let it train for a really long time, you get, voila, per pixel depth prediction that rivals what LiDAR can do directly. And as Karpathy notes, the difference between true LiDAR and false LiDAR is actually closing, so that the vision systems are getting really, really close to being able to produce false LiDAR images, which renders LiDAR just completely unnecessary at that point.
In particular, we have huge data sets of people driving cars. So when people drive cars and they steer the wheel, they're actually data labeling for you. They're showing you how to drive through any intersection or any other kind of place.
So here Karpathy talks about how people driving cars are actually doing data labeling, which is the awful, tedious thing that researchers normally have to do. And what a great thing that, us people who are paying for it are actually labeling their data.
We have probably the most interesting, largest data set of videos. These are coming from cameras. And so we've been really looking into some of these self-supervised techniques to speed up the process and to speed up the rate at which we learn from very little supervised data. So we don't have to collect like tens, hundreds of thousands of examples of accept, right, turn. We can do it. We prefer not to.
If people driving can label all this data, it means the engineers don't have to waste their time doing that. And that is a really giant advantage to having all of the cars that Tesla does on the road. What are my final thoughts on this lecture? Tesla is building from research at the forefront of image processing and neural networks and creating a monster of a deep neural network, or more accurately, many of them connected together, to create a machine learning model that can teach itself to drive. Not only is it more human for a car to teach itself rather than be told each element explicitly, but it's also more tractable. This is the only model I can see actually working. A machine that can extract its own training samples, work in a semi-supervised setting to teach itself, and then get the real-world experience, either through shadow mode or through betas, to learn to drive in a real-world setting. That, my friends, is pretty darn cool. Okay, I hope you found this episode enjoyable and informative and a little bit mind-numbing, perhaps. It was a lot of work to put it together because it's really hard to deal with all of these different things and explain it to everyone. Anyway, if you did enjoy it, definitely make sure you like and subscribe, and definitely also make sure you like and subscribe for the sexy mug. Still have 1 day from when this will be released, so you get on that real fast. In the meantime, ask me questions in the comments or at my email address, which is DrKnowItAllKnows@gmail.com. Till next time. Bye-bye.